So hi, everybody. Welcome to this very exciting official final presentation of the American Society of Civil Engineers Structural Health Monitoring Challenge. I'm really happy that we had 5 really nice submissions. I'd just like to thank you all for your extremely detailed and professional reports, which I've seen. I know it's been a lot of work, so it's really great that you participated. We have some members of the evaluation panel here right now. So Fernando Moro and Jean Lee are here. I think the rest of the Suzu Xu is also here. So welcome to you. Oh, Ellen is here as well. So actually we only have 4 out of 5 of the evaluation panel members. So welcome to you as well. And again, thank you to you for being prepared to be professional evaluators in this challenge. Yeah. So the structure of today is that we hear 5 presentations. We have an hour, right? So I've asked you to present 8 minutes each. I will, after 8 minutes, ask you to stop. I'm really sorry. I know 8 minutes is really short and it doesn't do justice to your work, but everybody who's here today has got access to the platform where your report is available. So in the worst case, just refer to your report for further details and just try to give a good overview of what you did. And we will probably I will probably do 8 minutes and then time for like 1 question between presentations. But I don't want to do a lot of questions because otherwise we might end up running out of time. I think most of us have to leave at 5 o'clock on the dot. So I'm going to stop talking. I'm going to ask Anmol to just share his screen and start the presentation, if that's okay, does anybody have any questions before we start? Okay, maybe quickly I assume everybody knows that the solutions are all available on the new WeDoWind platform, which I put in the chat. I guess you all know about this meeting because you've seen it, but just in case you've missed it, if you click on that link, you should be able to see the reports and then you can maybe follow them while you're listening to the presentations. Okay, so Anmol, over to you.
Hello, yeah, I will share my screen. Yeah, today I'm presenting my final results through a presentation because somehow I had a problem with my report. Okay, so I hope you all can see my screen. My name is Anmol Sharma and I welcome you to my final report presentation of ASCE-EMI Structural Health Monitoring for Wind Energy Challenge. And in this presentation, I will start with first my motivation and goal of this challenge. Then I will explain about the challenge and then the methodology I used in this challenge. And then I will talk about the machine learning model, which I used for the fault detections and their results for the pitch drive and for icing events. In the end, I will also talk about the classification algorithm after the detection I used. And the last one, I will talk about the deep learning model, which I used for early fault detection algorithm for the pitch drive failure. And the end, the conclusion and future work. So starting with the motivations, my motivation to join in this, to participate in this challenge was first by participating in this challenge, somehow I can help to reduce the carbon emissions and climate change, or to prevent the downtime and improve the wind turbine performance, and also to reduce the operational cost. Because yeah, with the help of AI, we can predict and prevent the failure. The goal of for this challenge was to first to figure out which sensors affect the failure, to detect and classify the type of fault, and the last one to predict the failure before it happens. So the first challenge was pitch drive failure, to detect pitch drive failure. What is pitch drive? Pitch drive is a part of a wind turbine which is located at the base of the blade. It is responsible for adjusting the angles to get the maximum output of a turbine, or output power of a turbine. A failure in this pitch drive causes a wind turbine to generate less power. The next challenge was icing events. What is icing? Icing is like the ice or the snow which located on the surface of the blades, and it's also it's a failure or a kind of failure which, because it affects somehow the aerodynamic imbalance, or and indirectly relates to the power generation of the wind turbine. So these were the two challenges where I focused on this part, on this challenge. The methodology I used for this challenge was first the data collections and the data preparations, and afterwards I analyzed the data set and pre-process for the feature selection and model training, and the end model evaluation. Data collections and information. The data set we got it from the WeDoWind was consist in HDF file. We had around 10 days of icing events and 12 days data set for the pitch drive failure. Each HDF file consists of 33 sensors data, which is shown here, and 5 kind of SCADA data consist of wind speed, power output, nacelle orientation, and turbine state. The SCADA data consists of the sensors were at 200 Hz frequency, and the SCADA data are in between 6.5 to 7 Hz frequency. So first, by analyzing the dataset, I observed that during the normal operation condition, the wind turbine behaves at wind speed between 2 to 4 meter per seconds, whereas the rotor speed between 40 to 60, and the power output at 2 to 5 kilowatts. And the sensor accelerometer behaves a recurring pattern during the normal operating condition, which mirrors the wind power and output, wind speed, and the power output behavior. And at the time of failure, it was observed that the wind speed was a bit higher, 5 to 10 meter per second, where the power output was 1 to 2 kilometer, which is abnormal, because normally with higher wind speed, the power output should be higher, and the rotor speed was stuck at 40 RPM. And by observing the sensor data, I was also observed that there is no recurring pattern, and there is a sudden drop in the acceleration sensor at the time of failure, which somehow relates that there is a failure in the turbine. There is some component failure. And for the icing events, by analyzing the dataset, first it was observed that at the time of icing period, the wind turbine producing almost no power. So maybe it was turned off or something, which affects somehow the accelerometers were also not showing any power, because the wind turbine at the time of failure was producing almost zero power output. But for the same speed, it was producing power output at the time of non-icing period. And by analyzing the humidity sensor, first it was observed that the humidity is higher during the non-icing period relatively compared to the icing periods. So one of the parameters are found that humidity sensor is interesting for the icing event, humidity sensors. The challenges I faced during the data analysis was the first, because of system crash, high computational load, and exploratory analysis limitation. Because of local machine or my computer was not so good, my system crashes with big data sets. And the sum of the possible solution I found were downsampling the data set, split the data set into chunks, or using parallel computation. But each of these solution have limitations. So in the end, the final approach was my downsampling the data I need to analyze for the full day analysis, or target specific analysis for specific time stamps, and also using rolling window analysis. For the feature selections process, I have used 3 feature selection process for the pitch drive failure and 1 for the model-based icing events. First was domain knowledge-based feature selection. By learning what are the sensors might affect the pitch, because we had in the beginning we had 33 features sensors for the 33 features for the sensor data for the pitch drive failure. And by learning which sensors affects the pitch drive failure more, I came to 10 top 10 sensors which are effectively affect the pitch drive. And then I used first correlation metrics to check how these 10 features are related to each others. And afterwards, I applied PCA to see to reduce those features. And for the icing events, I used model-based feature selection process. So this is the results where I got from the top 10 features when after the domain knowledge, that there are some features which are highly positively and there are some features which are highly negatively correlated to each other. And this is the results of PCA. After to combine those highly positively and highly negative correlator, I chose top 4 principal component, but for the later analysis I dropped this method because the problem for me I had was, is there some, if anybody has question? Okay, for me was that I was not able to recognize which principal component correspond to which sensors. For that reason I dropped this method. And the last one was model-based feature selection for isolation forest, in which I figured out that the humidity center is highly correlated for the icing and non-icing period, which we also saw in the analysis. The methods I used for the machine learning method I used for the pitch drive failure. For the fault, yeah, sorry.
Yeah, you've already had 8 minutes. I'm really sorry. Like, can you just go to your conclusion slide and we'll just have to read the report on the. Sorry about that.
Okay, yeah, I will show.
We have to stop otherwise.
Okay.
Maybe you can just give us a conclusion if you have a conclusion or a summary.
These are the 3 results I used for the pitch drive failure, for the fault detection, for the pitch drive failure, yes. PELT algorithm, isolation forest, and rolling variance using t-test. And for the classification algorithm, I used 4 different machine learning, supervised learning methods. And these were my results for the pitch drive failure and for the icing events. And the last, I have used deep learning model for early fault detection, in which I've trained the model on the normal. First I trained the model on the normal dataset and get some reconstruction error as a threshold. And then I have trained the model, test the model which consists of normal data and faulty data. And with the help of threshold, we were getting to see that if there are some anomalies already detected before the failure happened. And that's my, sorry for taking a bit of time. That was my final conclusion, that I was able to first work with machine learning and deep learning fault detection models, worked with high frequency data set during this challenge, and achieved fault classification. And my future work could be to handle more better high big data set, generalize across different data sets, and integration this challenge into a real-time system. Thank you.
All right, great. Thank you very much. Again, Anmol's report isn't yet available because he was sick. I've given him until the end of the weekend to submit his report. So if you have to wait until then to see the report. Does anyone have a quick question? It might be difficult, but anything?
I have a quick question. Thank you for your presentation. For the PCA, you show the plot, and I can see the vertical axis. I think it's a slide 17 or 16 on your PCA values, and you have how it's getting your information on the
this one.
That one, 14.
Yeah.
So, what was so I imagine. Yeah. So I guess what is your conclusion here? You got the first 3 PCAs, or what do you do with this plot?
I haven't, because I chose those 4 PCA component, but for testing I chose because of the method that when there is a sharp elbow bend in the variance, and then it's the way to recognize how many PCA component you want to choose. But later for the machine learning model, I dropped this method because I was not able to how to test it for if I want to check which sensors relate to the failure. With the principal component, I was not able to recognize.
That's good. Thank you.
You're welcome. Thank you.
Thank you. Let's move on. Can I ask Marcella to now start sharing the screen? I just want to point out that Anmol and Theo, you need to fill out the participation survey. It's mandatory, and you 2 haven't done it yet. So if you wouldn't mind doing that within the next couple of days, it would be great. Thank you. I put it in the chat. All right, Marcella, please go for it. We can't hear you say anything. If you're speaking, we can't hear you. Don't know whether you are.
Am I audible? Yeah?
There you're on now. You're on.
Can you see my presentation?
Yeah.
Right. So the solution for this challenge is entitled Failure Classification, the event wind turbine. During operation, use the PyMLDA open code. It's co-authored by myself, Marcelo Machado, Jefferson Coelho, Amanda Souza. We are from the University of Brasília. The PyMLDA is a framework that is being developed in our group. The idea is using dynamics response from systems where you could identify damage and quantify the damage and quantify the uncertainty associated with the damage. So our solution is based in this developing code. So the motivation, again, is to test this code and improve using this some experiment in real and complex systems. The objective then was identify these 3 types of failure who was proposed here in this challenge. So the solution for the classification damage in the event start with the data acquisition, some signal processing, feature selection, normalization. Classification uses some unsupervised methodology and the model evaluation. Sorry, just sign out, this whole process took approximately 8 minutes, so it's a very fast process that we are running Colab in a free version of these tools. So understand that the failure is based and allocated in the nacelle components, and from previous knowledge, you understand that the best sensors or more sensitive sensors to the damage is allocated close to the damage. So we think, before I go through all the databases, who was a challenge for us as well, we thinking some candidate sensor was the sensors on top of the turbine, also the one installed in the nacelle. And we also analyze in this, the 2 axes of the sensors represented the Y direction of vibration of the turbine and the X direction. So the sensors we are always analyzing zeta and Y direction. Thinking about the sensitivity of the sensors, we run some analysis to check how the sensors in the nacelle, that was the one that we selected to analyze first, how they capture the dynamic behavior of the systems, and we saw some pattern among the sensors in normal operation, also in failure operation. So for the analysis, we remain and use only the generator, sensor installed in the generator, because these sensors, we understand that they are responsible for, the generator is responsible for harvesting the system, so the sensors will capture the main variability or whatever happened in the system, the sensor would be able to capture some difference. The next step was reorganizing the data set, because we found some duplicated data in the data set available, so it remains untouched. The failure correlated with the coupling, and the normal operation we didn't change, and the failure related with icing balancing and rot icing, the duplicated one, we just relocated following the chronology of the data sets provided to us. After that, we started the feature selection process, and what we used was a few methodology based on the spectrum statistical methodologies. And what we found was they could extract the features. They have different amplitudes, and the difference between normal operation and failure operation, I just draw here the threshold to exemplify, was the sensitivity, the features could capture this variability, but was a very small difference. And what you thought that if we could zoom in or amplify this difference here and conserve the dynamic behavior of the failures change over time would help a lot. So that's what we did, and then we proposed to use this the damage index relative change. And as you see here, the difference between the non-normalized to the normalized features after apply the normalization increased a lot and helps indeed to identify and classify this damage. And that's what we did. So we normalize all the features that we can see here, and indeed we could scaling this difference between the operations. Among the 14 tests feature methodology we used, 8 was the more sensitive to the damage, and as you see here, we could normalize all of them, and they have the same scaling, so it would help in the classification. And that's how we'll build up our data sets. And then we have here 4 types of analysis. 3 binary when we correlate a normal operation and the failures, and also when we combine all together and try to classify the 4 conditions of the system. So these data sets here with all these 8 features that was more sensitive to the damage, we input in the unsupervised k-means algorithms and ask the k-means to classify for us in binary and also in multi-classifications. The k-means, after reorganizing our data set and classified for us, we could understand better by analyzing the dispersion diagram. Here are the features classified by the k-means. And we analyzing always in these 2 axes, and the y direction is at the directions of the sensors. Here is just a representation of a binary case. When we see in blue was the classification of undamaged or normal operation, and the other colors associated with the failure, in this case here for the coupling failure. For the multi-class, we also see some pattern here that the k-means provide us. And also here you see in yellow and in purple, yellow authorizing, and purple, the aerodynamic imbalance. And you see here also some pattern that we induce us to understand that if you input in these classifications algorithms, we could achieve a good classification through this process. We use 6 methodologies to classify our system. All of them returns a very good metrics with the outstanding by the SVM, and the SVM we just are demonstrating here. The confusion matrix is just proving and showing what's showing here in our metrics. The SVM return the classification of this confusion matrix is very low number of misleading classifications. This was for the binary case. For the multi-class case, we performed the same. With all algorithms, again, SVM could return us a very good accuracy and classify the 4 cases, these in multi-classifications, again, with classify very low number or rate of misleading classification as presented by the confusion matrix. So our final remarks that we could use and test the data set from event with a complex system in our framework. This is ongoing developing our research. We could propose some improvement in some the relative damage index to scaling this difference that was really helpful for the classification of these unsupervised and followed by these classification algorithms in binary and multi-classifications. All of them perform very good with FDM outstanding the algorithms represented by the metrics. And indeed, this challenge makes us think out of the box. We have a lot of ideas to improve this work, not only those 3, but we are starting implementing some different types of feature extracting, some also incorporating multi-data and multi-physics in this analysis. We use only the accelerometer data, but we'd like to improve and induce other physical informations to enhancing our analysis. I'd like to thank you everybody for your attention, our sponsor agency, also institutions, and indeed the WeDoWind to open this challenge and help us to go forward in our study. Thank you.
Brilliant. Thanks very much. Is there one question?
Hey, hi, Sarah. This is Ganesh.
Hi.
Hi. So I have a question on the pitch drive failure detection.
Yeah.
So I want to understand which I see that you are looking at the vibration data.
Yes.
I'm trying to understand, are you looking at the tower vibrations or?
Yeah. Sorry. We decided to focus mostly on the accelerometers installed in the nacelle. And we in the accelerometers, and then because we joined late in the challenge, we decided to use the generator because it was a lot to process and understanding. And yeah, we decided to use the generator accelerometers for the analysis.
And based on generator acceleration, you are predicting pitch drive failure. Is my understanding correct?
As well, yeah.
Okay. And
we understand that we should cover more sensors, but the time we had, this is the next step, but that's how we decide to perform the analysis.
I'm just trying to understand on what basis you decided to use acceleration sensor on the generator, because the pitch drive is in the front side and the generator is in the back side.
Yeah, but that was our choice because the generator is the one responsible actually to harvesting, and something happened in the system of the dynamic. That was our thought. The generator will capture because generator, is the component that you're harvesting the electricity. If something happened, he will be affected. That was our process of thinking in this case.
Okay, sure.
And why we chose this sensor.
All right, thank you very much. Let's move on to the next presentation so we have enough time. Well, thanks again for your hard work as well. I think Tia is the next one. Yeah, thank you. We're seeing the wrong screen. I think you're probably... Yeah. Perfect. We can't hear you. I don't know if you spoke, but we can't hear you yet.
Yeah, because I was muted.
Oh, yeah, okay.
Okay.
Great.
So, hello, everyone. My name is Theodor Varouxis, and along with myself, Ramin and Mahmoud help present our solution to this challenge. Our solution is titled an unsupervised damage detection framework for an operating wind turbine. Starting with the outline of the presentation, I'm going to begin with the introduction, then I'm going to present the data sets that we exploited, then I'm going to present the methodology utilized here. I'm going then to showcase our results for 3 different damage detection scenarios, the aerodynamic balance damage, the rotor icing case, and the pitch drive failure case. And then I'm going to conclude with some conclusions. So, critical infrastructure like railway, like wind turbines, like bridges, oil rigs, and whatever is critical for our day-to-day lives needs to be monitored. How you can do that is you can employ sensors, you can instrument the structure with sensors. The sensors actually give you information corresponding to the system current state. Then, using feature engineering, you can extract the information relevant to the current structural health state of the structure, and then you can use this information that you've extracted to perform structural health monitoring. Moving to the damage scenarios, we had 3 damage scenarios. The first one is an icing event caused by a cold wave that produced ice forming on the leading edge of the wind turbine blades. Then we have the aerodynamic ballast case where a roughness tape was installed in one of the 3 blades, creating an aerodynamic balance in the wind turbine rotor. And finally, we have the pitch drive failure, which is when the pitch drive failed after the pitch linear drive was replaced. Now, going into the methodology, feature engineering and feature selection in general has some steps. You start with data collection. then using the raw data, you preprocess them, you clean the data, and then you extract the relevant statistical features of your choosing. From those features, you select the features that are relevant or contain the most information related to your study. Using those features, you can input them in a machine learning model. In our case, it's an anomaly detection shallow machine learning model. And then the output of the model can be a damage indicator. So for the purpose of this study, from the raw acceleration data, we have extracted the time domain features. Then we used an unsupervised feature selection method, a filter-based method. And the output of the filter-based method was used as an input to two different clustering algorithms, an isolation forest and a density-based spatial clustering of application with noise algorithm. Moving to the first case, the aerodynamic balance, we've collected all of the data sets that correspond to that case and consider every case before the roughness tape installed to be the healthy state of the structure and every state after the roughness tape was installed to be the damage state. And we divided the whole the whole data domain into two sets, the training set from March 24th to August 17th, and then the test set or validation set from September 3rd up until January 21st. From all of the available channels, we selected 7 accelerometers. 6 of them were installed in the tower in the highest position corresponding to section here, section 5 here, and then we used the input from one of the main sub-bearing accelerometers and the wind speed input. And then for each of these sensor channels, we calculated the maximum, minimum, mean, skew, and standard deviation. These features were inputted to an isolation forest algorithm. The isolation forest algorithm yielded satisfactory results in terms of damage detection, achieving more than 95% accuracy. Now, moving to rotor icing, we did exactly the same process where we considered the data before the icing event to correspond to the healthy state of the structure and the data after to correspond to the damage state. So again, with a similar split, we decided to use the data from March 24th up until August 17th for the training set of the algorithm, and then the data from September 3rd up until December 20th for the test part of the algorithm. We used exactly the same sensor channels and features, and we inputted them to an isolation forest algorithm. The results of the isolation forest are more than satisfactory, with the binary classification being perfect. And finally, for the pitch drive failure, the pitch drive failure was not as straightforward as the previous two cases because you'd have more than two health states. And we've taken the following assumption. The 2 days before the pitch drive repair and before the turbine stopped operating are considered to be damaged, are considered to be corresponding to the damage state. This would be February 15th and 16th. The data before that, from January 22nd up until February 14th, are going to be the healthy state. And we've characterized the data after February 25th, when the pitch drive was repaired, to also correspond to the healthy state. This time, we only used the output of a single sensor channel, and we used this time series to estimate an autoregressive model. Then the features that we chose would be the damping gradations, minimum square error, and mean absolute error of the model residuals, and the mean of the acquired time series as an input to a density-based spatial clustering algorithm. The results of the algorithm are, again, satisfactory, with achieving almost perfect damage classification results. And finally, here you can see I accumulated the statistical quantities needed for the challenge. In the first column, you can see the damage detection accuracy with all of the binary classifications achieving more than satisfactory performance. And thank you for your time.
Perfect, thank you. Questions?
I have a quick question on the so all the results you show them are binary classification. Have you ever looked at multi-class case?
We haven't, as the main purpose of this challenge was damage detection. Damage detection is binary classification. This is something that we can look into in the future. What I would try to do coming from this was to try and use only the accelerometer used for the pitch drive failure and see whether we can use this one sensor channel to initially damage detection, so another binary classification for all damage cases, and then try and see whether you can do damage classification or damage identification. But at the moment, because there were only a few test cases where more than one type of damage were present at the same time, we only focus on damage detection.
Okay, thanks.
All right, thanks. Let's move on to the next presenter, who is Shun Wang.
Good afternoon, everyone. I'm Shun Wang, a PhD student at UPC Spain. I'm pleased to share our solution for this challenge. We developed an approach using variational autoencoders for winterband health monitoring with any normal data. This work was completed with my supervisors, Yolanda and Francisco. This presentation has 4 parts. Starting with the dataset overview, this timeline shows the key events in the challenge data. January, pitch linear drive replacement. February, pitch drive coupling failure and replacement. December, 2 events, isolate events and aerodynamic imbalance. Our goal is to detect 3 failures: broken flexible coupling, aerodynamic imbalance due to roughness top, and blade isolate. Where we had access both vibration and scatter data, in our solution we focused on vibration signals because vibration data offers higher frequency sampling and direct turbine monitoring. Here we use the 14 channels at key locations: pump, nacelle, main shaft bearing, and generator. These sensors can detect a problem across all important parts for the wind turbine. Now let me explain our method. We use the variational autoencoders to learn normal behavior. First, convert vibration data into key features. Then the encoder maps these features to normal distribution. Next, using sample from this distribution, the decoder reconstructed the original input features. The linear process is guided by 2 loss functions: reconstruction loss and KO divergence. The reconstruction loss mirrors the difference between input features and reconstructed features. The KL divergence ensures that the latent distribution close match normal distribution. For feature extraction, we extracted 2 types of features: time domain and frequency domain. After VAE model calculates the reconstruction errors, we also applied EWMA to smooth these errors. This smooth step can reduce noise and improve detection stability. As shown in this figure, our health index has 2 stages: training stage and monitoring stage. In the training stage, we use normal historic data to learn normal behavior. This stage involves data processing, feature extraction, VAE modeling, and EWMA smoothing threshold setting. The monitoring stage follows the same process, but use the trained VAE model to detect deviations from normal data. When the health index exceeds the threshold, the method can flag the potential faults. Most of the time, importantly, this method can detect any deviation from normal behavior, not just the specific faults in this challenge. Next, the experimental results. As mentioned, we need to detect the 3 failures. However, there is a critical event occurred on February 24th. The pitch coupling was replaced. This change requires us to use 2 separate VAE models. Model 1 trained on data before the replacement. Model 2 trained on data after the replacement. In details, as shown in this figure, the red mark shows abnormal periods. The blue shows normal periods. We split the data into training, validation, and testing datasets. Model 1 detects pitch drive failure using data before the pitch failure. Model 2 detects both imbalance and isolating events with the same training and validation depth. For each model, the training datasets are used to learn normal patterns and train the model. The validation datasets are used for setting thresholds. The testing datasets are used to evaluate performance using both normal and faulty data. Before training the model, we also take 4 steps to prepare our data. First, we filter out the data when power output is 0 and or negative to remove outliers. Second, we divide each 10 minutes timestamp into 60 samples. We calculate the reconstruction errors for each sample, then average them into one value for this timestamp. Third, we center the vibration data around 0 by removing signal biases. This helps with feature extraction. Last, we apply the minimum maximum normalization to ensure all measurements and features are on the same scale. Now we get the results. This figure shows health index from different stage for pitch drive failure. Green dots are training data showing normal behavior. Blue dots are validation data for setting threshold. Orange dots are test data for evaluator performance. Here, the health index exceeds the threshold, triggering an alarm at 14:32 on February 16th. The actual failure happened on 17:12. This means that we detected the problem nearly 3 hours before the breakdown. Our method also successfully detected the aerodynamic imbalance. On December 8th, the health index went above the threshold, correctly detect when the imbalance began. Similarly, on December 17th, our solution detected isolating events perfectly. Here, the health index clear jump above the threshold when the isolating began. For imbalance and isolating, the metrics and the performance metrics shows 100% accuracy. Our solution successfully detect all faults with no false arms or missed events. Computational efficiency is also crucial for real-world monitoring, so we counted the time taken by our method. Specifically, in the model inference, our method takes just 2.56 seconds to process data. This quick speed plus perfect detection performance make it critical for real-time applications. Furthermore, we put the health index between imbalance and isolate together and compare them. In this figure, the red dots are from isolate events. Blue dots are from imbalance periods. We found that generally the red dots generally labeled isolate show higher HI values, while isodynamics show present lower values. It matches with physical understanding because isolate affects isodynamics and blood weight distribution, which can result in bigger changes in vibration data and result in higher reconstruction errors in VAE model. So, but the grid highlighted periods show unusual patterns. We think this might be unrecorded isolate. The weather data supports this, showing low temperature and high humidity. But without the direct ice checks, so we can't be certain. If it is confirmed, we could use a simple threshold method to distinguish isolate and aerodynamic imbalance. Last, let me summarize our achievements for this solution. Our framework successfully provides early fault detection with 100% accuracy and real-time process speed. Most importantly, it only requires normal observation data for training. Before, in the data division, due to the pitch comment replacement, we treat the replacement and post replacement periods as two winter bands with different training data sets. That's because the component replacement changes the data patterns. So future work, we plan to develop the domain adaptation or domain generation method to better handle the component replacement. We also aim to integrate SCADA data with vibration signals to improve the detection performance. Yeah, that's it. Thank you for your attention.
Perfect. Thank you so much as well for your work. Does anyone have a quick question?
Hello. Nice presentation. I have a quick question. Could you clarify, maybe you've done that already in the presentation, could you clarify what's your health index? You said EWMA, right? So that's...
Yes, the smooth health index.
Can you elaborate on what exactly that index represents?
First we calculate the reconstruction error using VAE model. This means the deviations from the normal data. Then we use the EWMA to smooth errors. This is the final health index.
Gotcha. Basically the version of the reconstruction area.
Yes.
Okay, thank you.
Thank you.
All right, we have to move on because of time constraints. By the way, feel free to ask any questions on the platform as well. You can tag people, and so you can do it that way as well. All right, so last but not least, Zukai. I hope I'm saying your name properly. I'm sorry.
Yes.
Please start.
Okay, can you see my screen?
Yep.
Okay. Okay, hello everyone. Our group ID is 9. My name is Jukai Zhang, and I'm from Department of Civil and Environmental Engineering at Texas A&M University. Our team also includes Ted and our advisors, Dr. Nosha Driven and Dr. Tao, all from Texas A&M. For this challenge, we use this Aventa AV7 ETH Zurich research wind turbine as shown in the picture. Using the provided structural health monitoring data, our goal is to accurately distinguish between 3 failure events and normal operation, helping improve future predictions. Ideally, when we combine data from all these 4 events and classify them, we expect to see clear distinctions. Here we use different colors and shapes to represent each event and assume the data can be visualized in a 2-dimensional space. In this case, it should be 4 separate clusters. However, 2 key facts in the dataset may affect classification. First, each data file contains a 10-minute recording of health monitoring data, including a short period before and after the failure event, as well as the failure event itself. As a result, normal operation data may also appear in a failure event record. Second, multiple events can occur together, even if they are not the main cause of failure. For example, in winter, lead acid may happen alongside the blade aerodynamic imbalance failure. In this case, acid may be recorded in the dataset, but not explicitly reported. From this analysis, we make an important assumption. In the real data side, even with a perfect classification model, the named failure event will make up the majority of each clusters. Once we form 4 clusters, we label each one based on the most common event it contains. For example, cluster 0 here represents the normal operation data. Cluster 1 is a page drive failure, cluster 2 is the blade aerodynamic imbalance, and 3 is acid event. Now let's take a look at our model 1. For training, we selected 5 files from each event. Each contains the 10 minutes health monitoring data. After combining the data and apply necessary pre-processing, we trained the model using K-means. K-means is computational efficient, easy to implement, and works well when clusters have clear separation. Instead of jumping straight to more sophisticated models, we started with a simple approach and gradually increased complexity. Next, we analyze the event distribution within each cluster. For example, in cluster 1, here we use the abbreviations IPBN for different events. As we can see, blade aerodynamic imbalance is a dominant event. Therefore, we label cluster 1 as blade aerodynamic imbalance, as well for the other 3 clusters. To test our model, we used 10 files from each event to create a test dataset. We took 1 file at a time, removed its original label, and fed it into the model. This produced a distribution like the one shown here. From the results, we can see most of the data belongs to cluster 0. In the previous step, we assigned the page drive failure to cluster 0. Now we can compare our predictions with the original label to check if they are classified correctly. We repeated this process 3 times using different test data sets. After testing all files, we created a simplified confusion matrix. The event index follows I, P, B, and N. The accuracy here is 1.0, 0.33, and 0.75. As you may have noticed, the accuracy reaches 1 in some cases, but drops to 0.33 in others. Although the overall accuracy is 0.693, when combining all 3 data sets, this indicates that the model lacks robustness and struggles with certain scenarios. We believe this is due to limited training data, causing the model to underperform when encountering unseen scenarios. To address this, we decided to expand the training data set for Model 2 from 5 files for each event to 15 files for each event. We trained Model 2 using 15 files from each event and continue to use k-means for training. We tested with the same test data set as before. This time, the accuracy generally improved with the overall accuracy raising from 0.693 to 0.773. In conclusion, we have proposed a framework to classify the 4 events, achieving good accuracy and demonstrating potential for future predictions. And the next step is to feed the model more training data to enhance its complexity. Thank you for your time. I'd be happy to answer any questions you may have.
Brilliant, thanks very much. We have 2 minutes if anyone's got a question. So either everything was perfectly explained or people are dropping off to go to new meetings.
Maybe a quick question, if I may. Sorry. Could you explain a little bit more on the difference between the 2 models? Probably missed some of the details.
The main difference between 2 models is Model 2 have more training data set.
Gotcha. Okay. Cool. Thank you.
Thank you.
Let's conclude. Yeah, I just thank you to everyone for also sticking to the time, and we managed to have the 5 presentations with 1 minute to go, so that's perfect. The next steps are the evaluation panel is going to meet next week, and we'll make the decision and announce it by the end of February. We will also contact the solution providers for a paper, because we said we were going to write a paper with the results in, and so we'll need to coordinate that. If you're interested in taking part, then we'll meet and talk about it then separately, but probably in March. Yeah, so just a reminder, if you haven't filled out the questionnaire, please do that immediately, and Anmol, please submit your report by the end of the weekend so that we can look at the reports properly. And yeah, I think, Theo, you wanted to ask something?
Yeah, I wanted to ask something regarding the collective paper.
Yeah.
While doing some of the work related to this challenge, I had other ideas that are not necessarily revolving around damage detection. Will this be part of the paper, or can I publish something on my own on a later time?
I think probably both. I think we need to talk about what exactly we want to put in the paper and what we don't. And I think that's also, you should be deciding this. We should decide this together. So my suggestion would be I contact you all and we try and have a meeting and then talk about it. But I think there's enough content having these 5 solutions, maybe doing some simple comparison or something, and probably there won't be scope to put additional stuff in because there's already going to be quite a lot of details with 5 different methods. But let's meet and decide upon it together. Is that okay?
I understand that. I just was wondering whether this would be conflicting with the other paper or not.
Yeah, probably not if it's extra.
Okay.
Probably in the paper we're going to focus on like the idea of having this challenge and some comparison and some way of showing, okay, bringing these different teams together to focus on this one challenge actually has a value more than if you'd just done this work separately. So it's probably going to be more focused on that type of thing rather than any additional details. But I think the evaluation panel will probably talk about that in our meeting as well, and then we can decide how we like to do it, and then we can discuss that with the participants. So yeah, we'll be in touch as soon as we can. And yeah, then we can talk further. Is everybody happy? Is that okay for everybody? Again, thank you, everybody. Yeah, we'll be in touch soon.
Thank you.
Thank you.
Thank you.
Okay, thank you. Bye, everyone.
Bye.
Thank you.
Bye.
Bye.
Thank you.
Thank you. Bye.
Thank you.
Thank you. Thank you very much. Bye.
Bye.